What's the single simplest statement in C++? It's not return 0, it's literally just a semicolon. This is called a null statement or an empty statement. Now, why would you ever want a statement that literally does nothing? Because C++ syntax sometimes demands a statement even when your program logic doesn't need one. The most classic use case is inside loops, where all the actual work is backed directly into the loop's condition. Take a look at this while loop. First, the cn reads input from the standard input and checks if the read succeeded. If it did, s not equal to south checks if we found the word we are looking for. Because all the reading, updating, and logic happening right inside the while header, the loop body has zero work left to do. But C++ requires a body, so we hand it a null statement. And always comment your null statement. Writing this comment, null statement, proves to anyone reading your code, including future you, that the empty space was left blank on purpose, not by accident. Sometimes an extra semicolon is harmless. Look at this line. The second semicolon is just a null statement. The compiler ignores it and your program runs fine. But place that extra semicolon right after a while loop or an if condition and it will become a disaster. Look closely at that semicolon right after the while condition. Contrary to the indentation, plus iterator is not inside the loop. The loop body is actually that tiny null statement. Because iterator is never updated inside the loop, the condition stays true forever, trapping your program in an infinite loop. So always check your loop headers for accidental semicolons. Control structures like while loops or if statements expect exactly one single statement as their body, but what if your program logic needs to run multiple lines of code? A block is a sequence of statements wrapped inside curly braces. By wrapping our two statements inside curly braces, C++ treats them as a single compound statement. Blocks also establish scope. Any variable you declare inside a block only exists inside those braces. The moment execution exits the block, variables declared inside are destroyed. This keeps your program memory clean and prevents accidental variable naming conflicts. Here's a fundamental rule that trips up beginners in C++. A C++ block is not terminated by a semicolon. So after a semicolon ends, we don't put semicolon at the end. If you do that, you're not going to get an error, but you are creating a null statement. Also, did you know that you can write an empty block by using curly braces with nothing inside? Like in this way, we can just have an empty block, which is functionally equivalent to a null statement. However, using curly braces or commenting semicolon makes your code much clearer, proving to anyone reading that the empty loop body was intentional, not a missing line of code. Also, don't forget to like and comment and subscribe for more C++ videos. Ever written a loop in C++? Try to use your counter variable right after it, and your compiler acts like it's literally never seen that variable in its life. Yeah, you just got hit by variable scope. When you declare a variable inside the header of a loop or conditional, like this while loop, while integer I equals get number function call, that variable is on a strict temporary visa. The second that loop finishes, I gets wiped from memory. It's like a snapshot message. Once the loop is done reading it, it self-destructs. So what if you actually need that variable after the loop finishes, like to check where a search stopped? Then you define it outside the control structure. Well, this one has a purpose, because this one you're gonna keep calling the getNumber function until you get a result. This initialization of I is gonna get a number and it's gonna check that number if it's a non-zero variable, and it's gonna keep printing this as long as it's a non-zero variable. So if you put it outside, we are gonna get it only once. So now if the function getNumber returns 1, while I is always gonna be 1, so the loop will run forever. So we need another example for this. We define it outside the control structure. So if it's outside, you can check after the while loop finishes, or in the rest of the program, you can have access to it, and you can do whatever you want with it. So the bottom line is, variables created inside a control block die inside that block. If you want them to stick around, give them a home before the loop starts. Every app on your phone, from TikTok recommending videos to your banking app declining a purchase, is running on a basic conditional statements. In C++, decision making comes down to two big heavy hitters, if and switch. Today let's master the if statement. At its core, an if statement checks one thing: is this condition true or false? The condition always goes in parentheses, and C++ converts whatever is inside into a a boolean, true or false. If it's true, the code runs. If it's false, C++ completely ignores it and moves on. Now if you want a backup plan, you bring in the else branch. If the bank balance is at least $7, you get a matcha. If not, the if block is skipped entirely, and the else block takes over, so you stay hydrated for free. You can use single statements, but wrapping your execution blocks keeps your code clean and avoids nightmare bugs down the line. If you need to turn a test score from 0 to 100 into a letter grade, your first instinct is probably to write an infinite chain of if-else-if statements, but there's an insanely clean C++ trick that pairs basic if-else logic with a vector to do the math for you. Look at that else block. Instead of hard coding ranges for B, C, and D, we use integer division. Say a student gets a 75. 75 minus 50 is 25. In C++, dividing the integer 25 by 10 doesn't give you 2.5. It truncates the remainder and gives you a solid 2. And index 2 in our vector is C. So we handled failing grades with a single if and calculated every single passing grade in one line of math inside the else. We've got our base letter grades down, but what if we want to turn an 88 into a B plus or a 71 grade into a C minus without breaking our logic? This is where nested if statements and the modulo operator shine. Let's clean up and add braces for the ifs and elses. Now inside the else statement, we can add a nested if statement inside the else, and we can check if the grade is not equal to 100, so we don't modify it at all. And now we check if the grade modulo 10 is larger than 7, and we write letter grade plus equals plus sign. We add a character plus to the letter grade. 88 or 89 are gonna get A plus. And we add else if the grade again, add modulo again, where the number 10 is smaller than 3, to give the grade 70 or 71 or 72 minus, like A minus or B minus, etc. So now when I enter the grade, and here I made a mistake because I should have added it inside this block. So it should be like this, and if we remove this one, it would work anyway. We can keep those without curly braces. So now everything looks clean. I took input from the user to get the grade, so we can record it. Let's record 61. I would get D minus. If I take 72, I get C minus. If I record 78, I would get C plus. So the grade modulo 10 isolates the last digit in the number. If a grade ends in 8 or 9, 88 modulo 10, we are gonna get an 8 as a result for this operation, which is greater than 7, so C++ will append a plus sign to the letter grade. And so far that's how the logic works. But there's a fatal bug hidden in C++ conditional blocks that catches almost everyone. Let's cover that next. If you come from Python, C++ is waiting to trip you up with this subtle bug. So notice how the else doesn't have any curly braces. Without explicit curly braces, an else statement only controls the first line directly beneath it, which is only this. So those two exist by themselves, and this one works by itself, so they are not connected together. And because those braces are missing, the second if statement to check for plus or minus sent inside this else block. It runs unconditionally for every single score. This one will run anyway. That means a failing grade of 31 gets assigned an F first, and then the code immediately slaps a minus into it, giving the student an F minus. So don't rely on formatting, always use explicit curly braces for your conditional blocks. Even if it's just one line today, it saves you hours of debugging tomorrow. And as you can see how I made this mistake because I mixed braces and not braces together. But in this way we know exactly what's happening, so we don't really make a silly mistake. When you nest an if statement inside another if, you will often end up with more if branches than else branches. This creates a famous programming pitfall known as the dangling else. The big question is, when you write a single else at the bottom, how does C++ know which if statement it actually belongs to? In this example, it looks like the else is connected to the outer if because of the indentation, but in C++, indentation means absolutely nothing to the compiler. C++ resolves this ambiguity with one simple rule. Each else is automatically matched with the closest preceding unmatched if. That means C++ physically attaches that else to the condition B for this if, completely ignoring your indentation. If you aren't aware of this rule, it leads to subtle logic bugs where your code compiles with zero errors, but executes the exact opposite of what you intended. Let's look at a real example next. This is an example of the dangling else. Suppose we are adding plus or minus modifiers to the student grades. We want grades ending with 8 or 9 to get plus, and grades ending in 0, 1, or 2 to get a minus. Here's how a programmer might write it without curly braces. First, let's look at what happens when a student gets 75, which is a solid C grade. First, 75 modulo 10 is larger or equals 3, which is true. Then if 75 modulo 10 is larger than 7, which is false. So it will go inside this else statement because C++ doesn't care about our indentation. So this else is basically like this with the correct indentation visually. Yeah, so C++ will go inside this else and it will add a minus to the C grade, which is wrong. And in fact, every grade ending in 3, 4, 5, 6, or 7 gets an unintended minus sign to force C++ to attach the else to the outer if statement instead of the inner one. We enclose the inner if statement inside a block using curly braces. So we highlight this and now we can wrap it with curly braces. And now we have the outer if has this else. So never rely on indentation to structure your conditional logic. Always use explicit curly braces around your execution paths to keep your C++ code completely bug-free. If you need to check a single variable against a bunch of fixed options, say like parsing text character by character to count every vowel, your code can get ugly real quick. Chaining 10 else if statements works, but it's slow to read and clunky to maintain. That's where C++ switch statement comes in. And here's how it works. So we have variables for different counters for each vowel in a word. And we are taking input with a while loop. We are taking input stream inside the while condition. And inside it we have a switch statement. And inside the switch we are checking if the character we entered is a vowel and it will increment it. And it doesn't count vowels in a word. It only counts one single vowel, which is one single character. So C++ takes your variable ch, evaluates it, and instantly jumps straight to matching case label. So if it's an A, it will go inside this case A and it will increment the count. And there's a break. That break statement at the end of each case. Without break, C++ doesn't exit the switch. It falls right through into the next case below, executing any code that you didn't intend to execute. And there are 3 strict rules on case labels, and violating them will cause errors. The first one is the non-integer types. You cannot use floating point numbers like 3.14 or string literals as case labels. Cases must evaluate to an integral type like integer, character, or an enum. So trying to use a string inside a switch will get you errors. And number 2, non-constant expressions. Even though ival is an integer, it's a variable. Case labels must be constant expressions known at compile time like literal numbers or const expression values. So if you add just a const expression, it will not complain anymore. Or if you just add 42, it will not complain. And adding duplicate labels, like in this example, if we add another case A, we would also get an error because the case A has already been used. And why is C++ so strict here? Because at compile time C++ uses these constant integer values to build optimized jump tables, making switch execution insanely fast. What if you don't want to separate counts for each vowel, but instead you want to trigger one single action for any vowel? You don't need to duplicate your logic. You can stack case labels together. Since there's no break between case A or case E or I or O or U, then execution falls straight down until it hits ++ vowel count. and then break. And what about non-vowel characters? That's where default label comes in. If none of these cases match, execution jumps directly to default. And pro tip, always include a default label, even if it's completely empty. Adding default and just break signals to other developers and static analysis tools that you deliberately considered and handled cases rather than just forgetting them. What happens when we don't add a break after each case? Let's run the program and see what happens. So if I enter just a, as you can see, it has incremented all the vowels. So when ch matches a, it's going to increment a count. And then if it didn't find any break statement, it will also increment c. So as long as it doesn't hit any break statement, it's going to keep going into the other cases. What if ch isn't a vowel? Then we can add just a default and we can do something here. It shouldn't be empty, so you should add a statement inside it. Execution in a switch can jump across case labels. When execution jumps to a particular case, any code that occurred inside the switch before that label is ignored. What happens if the code that is skipped includes a variable definition? The answer is that it is illegal to jump from a place where a variable with an initializer is out of scope to a place where that variable is in scope. So this initialization might get bypassed. This one is fine because it's not initialized. So here it is still in scope, but it's uninitialized. So if this code was legal, then anytime control jumped to the false case, it would bypass the initialization of file name and ival. Those variables would be in scope. The code inside the false case can use these variables. However, these variables would not have been initialized. As a result, the language does not allow us to jump over an initialization if the initialized variable is in scope at the point to which control transfers. If we need to define and initialize a variable for a particular case, we can do so by defining the variable inside a block. So we can wrap it in a block and move the break outside the block. This way we are ensuring that this variable is out of scope outside this block. So now we don't have access to it in the false case or the other case.